In a heterogeneous computing environment with multiple CPUs and GPUs, it is common to have different versions of code to perform the same task on different devices. Conventionally, a task might be divided into many subtasks before assigning to computing devices. Each subtask is handled by a thread being forked by the master thread. Although representing the same concept, some platform-specific data structures are forced to be built for each computing devices due to different implementations. After assigning the tasks to threads being forked, the master thread must wait for them to complete the computation and join before further processing. The problem arises when the computation power differs in those devices. When a device failed to finish its task in time, all other threads need to wait for it. This results in resource underutilization. A naive way to relieve this issue is assigning the tasks in a non-uniform manner. Programmer can assign different number of subtasks based on some heuristic. However, this heuristic not works when the computation time is not predictable, especially in the case of irregular processing. The branch divergence affects the performance on most MT platforms including GPUs. Besides, the degree of branch divergence in ray tracing algorithm dramatically increases as time goes on. The performance of GPU decreases, resulted in unexpected waiting for GPU devices. To fully utilize all computation resources, we proposed the high-level task model. In this model, we do not build the platform-dependent data structure when tasks are assigned to each platform. The platform-dependent data structures are built until the corresponding computation devices are ready. This is similar to the just-in-time compilation. When a device is overloaded, the extra tasks can be reassigned to other idle devices with little overhead. Now we can freely exchange tasks between devices. We further propose a centralized task management for multiple devices, the heterogeneous queue. In the heterogeneous queue model, all tasks are placed in a queue. When a device is available, it pulls a task from the queue and executes it. There will be no idle devices until all tasks are processed. All resources are fully utilized. The effect of maximized device utilization can be observed from above figures. These figures represent the GPU timeline when rendering in traditional threading model and the heterogeneous queue model. The purple area represents GPU busy, while the white one is for GPU idle. We can see that in the heterogeneous queue model, the GPU utilization is much higher than traditional one. We can even sort the tasks based on their characteristic. Different devices pull their tasks out from different ends of the queue. Tasks that cause little branch divergence occurrence are suitable for GPUs. By sorting the tasks, GPUs will have higher chance to execute tasks that are suitable for their characteristic, and thus increase the overall performance.